Today we will show you some petrologic modeling and geochronology on Paleoproterozoic migmatites that outcrop in Morocco. The accretionary history of the anti-Atlas terrane is still under debate, and it includes several questions, including, for example, the age and nature of the basement of all the terranes that were involved in this history. Our contribution would be the timing and the pressure and temperature characterization of the migmatization event that is preserved in some paleolithic migmatites that outcrop in southern Morocco, in northwestern Africa. In this area, you can see several inliers, and in all these different inliers, up to six different events have been distinguished. All of them are made of different units that have been grouped under the so-called anti-Atlas supergroup. And the rocks that we have studied outcrop in the Zenaga inlier. This inlier is located below the major fault of the anti-Atlas and is attributed to the West African Craton. In this more detailed map of the Zenaga inlier, we can see that the complex, the terrain is dominated by paleolithic rocks, by schist and migmatites that are represented in this light pink. And these migmatites are intruded by granites and granodiorites of different ages, and particularly those that are close to the area where we made the sampling are 2,040 million years. So Tonian ages. The outcrop scale is quite, at the outcrop, the different domains are quite heterogeneous, and this heterogeneity is also reflected in the thin sections. And here we can see that we managed to distinguish at least three foliations, a relict one, scarcely represented, highlighted here in yellow, a second foliation, which is defined by prismatic sillimanite crystals, and a third foliation, which is mostly defined by fibrosillimanite crystals. In these more detailed images, we can see the shape of the prismatic sillimanites together with garnet and together with biotite and ilmenite. And the three foliation is mainly composed of this fibrosillimanite surrounding also the prismatic ones, and plagioclase together with muscovite, biotite, and other minerals. And what we can also see in these images is that the quartzo-feldespatic domains, the typical ones, are absent. We perform a geochronological uranium lead study in zircons using laser ablation. And here you can see a representative sample of the zircon crystals that we analyzed that exceed the classical oscillatory igneous zoning. We found that these data reflect a really very homogeneous population with almost about, with no inherited ages. And most of these ages, when we plot them in several diagrams, reflect to be older than 2,050 million years, so Triassian ages. And the mean age from a coherent group of 80 zircon grains has been estimated at about 2,086 million years. When plotting the Concordia age, we got 2,076 plus minus 4.6 million years, and this age is attributed to the age of the migmatization. We also studied the mineral chemistry in garnets, and what we got was no core to ring variation, so really quite flat profiles. And we interpret that this homogenization could take place during the high temperature event. In order to perform a comprehensive thermobarometric modeling, we first examined the amount of ferrous iron that we needed to include to model the rocks, because what we got from the lab were really, really high proportions of iron in weight percent. For this, we built several pseudosections, TX pseudosections, plotting a 0% of ferric iron to the left and the maximum of the analyzed value for each sample. In this case, this mole percent corresponds to this 3.32 weight percent. And checking with different temperatures, we got that at 750 degrees Celsius, we could see how garnet was stabilized outside the kyanite-bearing fields, in the sillimanite-bearing fields, which we are interested in, and also muscovite appears. Then we set the maximum ferric iron for the bull rock composition in order to calculate the next pseudosections to the half of the analyzed value. And we also examined the amount of water that we needed to introduce into the system in order to check to be sure that the melting process had the correct amount of water. We know that in typical pylites, like rocks, which are aluminum-rich typical pylites, the H2O saturation, so water saturation, can be really low at low temperature, at low pressures, and can produce water-saturated melt, which is exactly what happened to our rocks. We found that the solidus, which is this line represented in orange, is above 660 degrees. And we just need about 10% of moles, 10 mole percent of water for the rock to begin smelting. Then, according to our paragenesis, the melt produced would be or was water saturated and also liberates free water. Why? Because in this field, which is the only one that is consistent with the natural observations, we try to add the amount of corresponding water to the rock and build the different diagrams, and we didn't manage to reproduce the natural observations with undersaturated melt conditions. Then it doesn't matter if we use 10, 20, or 50, or 100, that we get the same results, but the melt needs to be water saturated. So we set water in excess. For this, with this data, with the half of the amount of ferric iron and the water in excess, we calculate a pressure temperature pseudosection. And we saw that, well, the blue line, above the blue line and below the yellow line, we have kyanite and cordierite-bearing fields, which are not of our interest. Then we can reproduce our natural observations in these orange fields, where sillimanite is stable together with several phases. In order to check which could be or inferred at least thermal peak conditions, we plot the calcium content in garnet and also the magnesium content in garnet. And both fields intersect in this little area shaded in blue at about 8 kilobars and 760 degrees. Then the rocks continue retrogression, crossing the garnet outline, crossing the plagioclase inline and the muscovite inline, and crosses the solidus at about 5 kilobars and 650 degrees. Because of all this, we think that these paleolithic migmatites may represent a leucosome that could have derived from a previous segregated melt, and just about 10% of water is enough to melt this rock. The melt produced is water saturated, and the thermal peak conditions have been estimated as 8 kilobars and 760 degrees Celsius. And the migmatization age has been set at 2076 million years, and this is in accordance with the nearby intrusives, And the next step, besides guessing the pre-migmatization pressure temperature evolution in these aluminum-rich rocks, is proposing an evolutionary model for up-to-date, the oldest known rocks in the anti-Atlas belt. And just to conclude, I want to say thank you very much to Mike Brown for his huge contribution during these 4 years, and take the opportunity of the birthday of the MSG to also say thank you and congratulations for his Barrow nomination to Roger Powell, and tell them both that thanks to their work, they too, as a representative sample of all the people that has hugely contributed to this, thank you, because for us, everything was easier thanks to your work. And this is all.
Great, thank you. And yeah, indeed, lots of thanks to great people in metamorphic petrology. Very interesting talks. Are there any questions for Alicia? Just lots of applaud for your talk.
Oh, wow.
And well, I have a quick question. So you said that you had way more Fe2O3 than like in your rock you analyzed more than you used for your modeling. Do you have any idea why there was such a difference? Is it kind of like a secondary alteration, or is it an analytical problem?
Even in apparently fresh rocks, this is quite usual, because everybody, when we go to the field, we try to check for the best samples and really don't know where does it come from, because there is not that much modal amount of chloride or things that can point to this. But I really didn't manage to reproduce the natural observations with that amount.
Well, yeah, I guess if lots of people have it and the rocks are fresh, then that must be something sample related. Yeah, anyway, I think any other questions, anyone? Just lots of people saying great talk, so no questions. I think we're all a bit desperate for a coffee.
Yeah.
So I think as long as there is no question now, I think we will go into. Well, there is one question. How mobile do you think the melt is? Could any of the melt have come from outside?
Possibly, yes. It's that what I don't know how to model now is it will be another of the key questions.
Yeah.
And really, we think that most of the samples in the outcrop could represent former leucosomes. Mm-hmm. So these rocks seems to have been already melted.
Yeah, but that goes on to the next question. There's a question of like, how much melt do you think was produced? So when you say you have like leucosomes in the outcrop scale, I guess that was probably quite a bit. Or do you have any kind of like, can you infer this from your modeling, like the amount of the volume of melt?
I don't have it, but I will go back to the outcrop and check all these kind of things, because when you get a few samples and you think it's enough, it's never enough.
It's never enough.
And now I really need to give a lot of these answers to my curiosity, and we will do it.